So now we're going to try and apply differentiation to some real-world problems. Well, in this case, the real-world problems that we're going to do are really going to be limited to geometry. But these could be extended to real-world problems. But we're going to just take a look to get a taste of what we could do with the differentiation as far as an optimization problem. So what are we talking about with optimization? We're saying that given some quantity to be optimized, and we're saying optimized, we mean either maximized or minimized, how can we determine its optimal value when subject to certain constraints? So there's some quantity that we want to maximize. So here it might be we're trying to maximize area or volume, or if we did a business problem, we might be trying to maximize profit. Now, all of these things, you could probably maximize them going to infinity if you could choose any variable values that you wanted. But the idea here is we're going to have these constraints. And so within the constraint, how do we get the optimal value? Well, the way we're going to do it is we're going to take the problem and formulate it as an extrema problem. We've done lots of those. So once we get it there, it should be relatively easy, but the hardest part is getting it there. All right, so let's take a look at a classic example, really the one that everybody looks at first. And it makes an important statement, this example. So find the dimensions of the rectangle with the largest area given that it has a perimeter of 20. All right, so you know that you have a perimeter of 20 to work with. How do you orient the lengths of the sides to get the largest area? Will you even get different areas from rectangles with different perimeters? Well, you will, and we want to see how we should figure it out to get the largest area we can. Okay, so the way we're going to do this is we're going to start by just trying to figure out what exactly are we trying to do? What are we trying to minimize or maximize? All right, so I can see that we're obviously trying to maximize area. You want to be clear about what you're doing and specify it, because in a more complicated problem it won't be obvious. We're so obvious. All right, so then what I want to do is I want to figure out what variables I should be considering here. Well, if possible, it's a good idea to sketch it. So in a lot of the geometry problems, we will be able to sketch it. There are some problems where you can't make a sketch, you just have to lay out some variables. So I'm going to say that the things we're allowed to choose here are really the two sides of a rectangle. So I made a generic rectangle called one X and one Y, and I could have called it whatever I want. And so now that I have that, I'm trying to find what values I should let X and Y be so that they, one, fit the constraint of having a perimeter of 20, and two, give me the maximum area. All right, so the next thing I'm going to do is, I had said that I want to maximize the area. All right, so I need to come up with this quantity that I'm trying to maximize. I need a function for that quantity. So, and this is going to be called an objective function. So I'm going to say, okay, the area A for this situation is obviously going to be X, Y to get the area of the rectangle, X times Y. Okay, that's good. So I've created my objective function. All right. Now there's only one real big issue with my objective function there. And that's that it has two variables, X and Y. We would like to get this so it's a one variable function, and that's what we're going to go and look for a way to do. And the way we're going to do that is look for some sort of constraint or relationship. Well, there was a constraint given. The constraint given was that the perimeter has to be 20. Well, the perimeter of this rectangle, obviously it's also x up here. I'm sorry, it's also y up here and x up here. So we have 2x plus 2y. So we have 2x plus 2y equals 20, or if we divide through by 2, then we'll get x plus y equals 10. All right, so there's our constraint. X plus y equals 10, or if I want to think of it another way, y equals 10 minus x, if I want to phrase it that way. Okay, so now the idea is I have my objective function, a equals xy, and I have a constraint that y equals 10 minus x. All right, so this tells me two things. I should be able to now get a into one variable by eliminating, say, the y and getting it in terms of x. And the other thing is I should look right here. Obviously, in a realistic problem, even in the realistic problem that's geometric here, we can't have certain values of the variables. So I'm not going to be talking about 0 or negative lengths here. So I know that the only thing that I can do with x here is x has to be between 0 and 10, and it can't be either one. So that's the domain of x is 0, 10. All right, that's a good thing to know, because we don't want to give some sort of answer that doesn't make any sense because the values don't make any sense. Okay, so now I'm going to take a and I'm going to put in the y as 10 minus x. And I'll actually just multiply it out, and I'll make it clear that now it is a function of one variable. Okay, so that's really good for me now. In fact, now is when I'm able to actually convert this into the problem of maximize a of x equals 10x minus x squared on 0, 10. So I just want to find the maximum value of this area on this interval. And I know I can do that by all the max-min techniques that I've looked at before. So I'm just going to go ahead, and I want to find a max-min, so I'm going to need the derivative. So that'll be 10 minus 2x. And then what I would do is I'd look for, again, where is the derivative 0? Where is the derivative undefined? Well, the derivative is 0 when x is 5, if I set 10 minus x equal to 0. And it's not undefined anywhere. So I know I have a critical number at 5. Okay? So now I want to think about what values I'm allowed. So normally I would make a number chart for a prime, but this time it's going to be a little abbreviated because, again, I can only go from 0 to 10, not including them. So I'm going to put open circles there. And then I'm going to put 5 in the middle of there. All right. And so if I want to know what's happening to a, I look at a prime and its sign. So now if I go back here and I put some values in. So if I put 1 in, then I obviously see that the derivative is positive. If I put, say, 6 in, I get 10 minus 12, I get negative, telling me that here a is increasing and here a is decreasing. So what happened? Well, I must have topped out at 5. So 5, I obviously get a relative max at 5 something. Okay, and again, since I could get my area back here was 10x minus x squared. If I put in 5, I get 50 minus 25, which is 25. Okay, now I'm actually looking for absolute max or min, in this case a max, but look at it. It's always increasing before 5 and always decreasing afterwards, so this actually has to be the absolute maximum. And this is going to give me my answer. So I want x to be 5, y is 10 minus x, or 10 minus, put in 5, or 5. So the dimensions that I'm looking for to get the maximum area are 5 by 5. That is interesting because what we're actually saying is this should be a square. And that's an important geometrical fact, that if you have a certain amount of perimeter to deal with for a rectangle and you want to get the maximum area, you create a square. So that's a well-known principle that we just showed to be true, and gives us some good insight into, why squares are used to maximize area.